In this video, we're going to go over the Lab 2 Vertical Jump Center of Mass Kinetics for KNH 381 Lab for Biodynamics Lab in the summer. To start off, make sure you have your sheet pulled up, mainly just the counter movement sheet, counter movement jump Excel sheet. If you want to have the worksheet pulled up, you can have that pulled up as well, but at least have this pulled up so you can, the Excel sheet pulled up so you can just follow along with the calculations with me. So the first thing we're going to do is look for where the first movement occurs during this jump. We have force, we have time, we have some variables that just match up with the table here, and so on. We're going to make sure that we find the starting point first though. So that's when force starts to dip a lot. It's kind of hovering right now around 780, 770s. Just keep on going, you know, 770s, 780s here. And looks like it goes up a little bit. Maybe that was me raising my arms up. It does that just by raising my arms. Okay, yes, and then it starts going down, 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 down. All right, so it looks like somewhere around here-ish or so, yeah, 780s, 770s, it starts to go down. To figure that out, I want to know where's a good cutoff point, and for that I need body weight. So let's find the body weight by entering a function in here. Entering a function in Excel, Google Sheets, whatever you're using, everything always starts with equals. And in this case, we're going to do the average function. Just the average. And we're going to do this for about half a second. So I'm using Shift and I'm just going to tab down. If you want, you can just highlight with your mouse. It takes a little bit longer, a little bit less precise. So I'm looking for half a second right here. 0.5, that's half a second. And we get 778.07. All right, so that will work nicely. I'm going to go search for that. That was around 0.9 something. Okay, yep, 778. So about right here is where movement in terms of the counter movement, the down motion starts. So I'm going to cut it right there by adding two rows essentially. And those two rows just make it easy to jump between the top and the bottom is the main thing. And now we need to figure out, do we have everything at the end? So we can go ahead and take a look. Up. Yes, we do. We have when force is 0. When force is 0, the person has left the force plate. So we have that. And right now that occurred about 1.907 versus 0.959. So that was long enough for the jump to take place, or at least the movement of the jump, not the flight portion of the jump to take place, but enough for the movement of the jump. So before we get started with doing some calculations here, we're going to do a few boxes to make sure. We're going to enter some information up here at the top so that it's easy to follow along. So our first one's going to be net impulse, or sorry, not net impulse, impulse. And then we'll do center of mass velocity, center of mass position, kinetic energy, KE works, potential energy, total energy, power, concentric work. Nah, we can leave that one off since we're not doing the whole row, or sorry, the whole column. So we can leave that one off. All right, to start, we're going to be doing impulse, and we need to get some initial things figured out. Impulse is going to start at 0 for us because we're not moving, so no change in velocities occurring there, no change in force is happening at that point. So we're just starting at 0. Initial velocity also 0. Our center of mass position initial is actually on our sheet given to us. It's just my center of mass side. I was the one that did this vertical jump. Just taking that 1.8 times 0.5618. So we can just enter that 1.01124. Great. All right. So we're going to do the impulse now. And to do that, we need a couple of things. We're going to do, if you recall, impulse is force times time. And we're not just going to take this force times time. We can't do that. We need the change in force between 2 points and the change in time. We're going to find the midpoint between two measurements of force and the time between those two measurements. So starting off, we'll type equals to, and we'll do the one of this row, and we're actually going to do one thing with this, minus, we're going to subtract it from body weight. And then we're going to do addition or plus, and instead of the one that's in that row, the one that happened prior. And same thing, we're going to subtract from body weight, which is G2. So I just typed in G2 there. So what we have here is we have this minus this plus this minus this force minus body weight. That tells us how much above or how much below body weight these two forces were that we're adding together. And then from there, we'll divide that by 2. So that finds the midpoint of those two, between those two measurements. And then multiply that force times the change in time. And the change in time is at least constant for us. It's just, in this case, it's 0.96 minus 0.959. That's just 0.001. So we can type that in. Since it's constant, between every measurement is 0.001 seconds. Great. And if you're not familiar with Excel or Google Sheets, if you bring your cursor right over this bottom right part, it changes to a different style cross, and you just double click it. Puts everything on. Oh, sorry. Redo that. Undo that real quick. I meant to put dollar signs in here. I need to put dollar signs in because I need this to continue pointing at body weight. If I just did that like I just did, it would go the next row down, next row down, next row down, and so on. We don't want it to do that. All right. So that's good. This is impulse. And actually, I'm going to get rid of this one that happens at 0 since we're off the plate there, or I'm off the plate there. So we can get net impulse now. It's going to be equals to, we'll type in an actual function that's baked into the program here. We'll just sum up all of that. That gets us 208.73 Newton seconds. All right. Now we need to get center of mass velocity. Now to get velocity, we need to we need to convert impulse into velocity. If you remember, impulse is equal to the change in momentum. Change in momentum, mass times final velocity minus initial velocity. And if you rearrange that, what this turns out to be is impulse divided by mass plus velocity. So equals to the impulse divided by, actually we'll do this one first. I'm just going to take this body weight up here and divide by 9.81. That gets us kilograms, so I don't have to type it in every time for some later stuff. So I can always point it up there. All right, back to center of mass velocity equals impulse divided by body mass, and then plus center of mass velocity, which is just the previous center of mass velocity. And before I drag down, put those dollar signs in for, again, the mass. Not any of the other ones, just the mass. Again, that makes sure it always points to that. drag that down, and as I'm doing my counter movement, you can see the velocity is increasing. Not very, very fast, but it's changing. 0.14 meters per second here, 0.25, 0.3. It's going down, and eventually it will slow down about here-ish. Yes, 0.659. That's minus 1.659 meters per second. And then it's turning around. And then I just skipped a little bit past it. Right here, it turns over entirely. Goes from negative to positive, and then propels myself, or I propel myself until I leave the plate. Now, actually, the max is right around here-ish, 2.763. It looks like 3.5. Yeah, 3.5. Here's about where actual max is, but I'm still not off the plate yet, so I'm off the plate here, and I'm below body weight, so it goes negative. There's a slight negative in there, so it decreases it because there's less of my mass that's able to push at that point. But we can point takeoff velocity to that. Great. And then we need center of mass position. Now to do this, we're going to actually need to do the area under the curve of velocity. Thankfully, we don't have to do any subtraction type craziness like we did with the impulse. So equals to this one plus this one, divide by 2, so again the midpoint between those two, multiply by the change in time, 0.001. Make sure you get that time correctly in there. Oh, sorry, and then we need to add in the center of mass position, the previous center of mass position. So between these 2 points, my position changed less than a millimeter. It's so insanely small, it's very negligible. But here I don't need to do any dollar signs to point to anything. I can just drag down like so. And I'll use page down. So looking at this, it's going down. My center of mass is actually moving down. And it bottoms out, looks like around 0.51, so about a little over a half meter from already being a meter high. Drops by about half for the preparatory, the downward counter movement phase, and then it starts going up. We can get rid of that last one. Awesome. Great, now we have kinetic energy, potential energy. These kinetic energy is 0.5 times 0.2 mass in kilograms, and then multiply by the current velocity squared. Sorry, couldn't see my keyboard for a second. There we go. And before I do the drop down, we'll do dollar signs on that mass. Okay, and then potential energy. This one is mass times gravity times height. Mass times gravity is just your body weight in newtons. So that makes that one easy. We'll do equals to body weight, and then multiply by the height. Now what's the height? It's center of mass position. Center of mass position. Okay, and then before I do the drop down, dollar signs. Drop down, and then total energy. That's just potential energy plus kinetic. No dollar signs needed on this one. So let's just take a quick gander at this. So we can see it's not changing too much at the outset, even though force is dropping. Not changing too much. Now it starts dropping. Dropping. Okay, turns around 398-ish. as it should about here, because this is where velocity turns over, and actually center of mass position also bottoms out right here, so that's where it should reach its bottom point, because here we have kinetic energy changing over from a negative to a positive, or almost, in between there. It's zero for a fraction of a second. We can't even measure. Even at 1,000 hertz, we can't even measure that. And potential energy is the only thing that's there at that time, plus some energy that is stored in our tendons and our connective tissues, that sort of thing, from eccentric contraction. Oh, sorry, and then I didn't go to the end, but we can see it goes up, 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 and it's increasing, increasing, increasing. Awesome. And then power. Power, this one is force times velocity, the current force times the current velocity. So force times velocity, and the first one's going to be 0, because velocity is 0. Then we'll do the drop down. Great. So we can see it's negative because we're going in the downward direction, or I'm moving in the downward direction. Here, page down, make it a little bit easier. And right when I bottom out, it turns over to a positive, doing positive work rate, or positive energy change in energy, or transfer of energy. Power is increasing, increasing, increasing. Looks like it peaks right about here. I'm kind of pointing some of these out because they're on here. But we're not actually completely over yet. We have our velocity is not peaked yet. Velocity peaks right about here-ish. So a little bit later, not too much later, but a little bit later, before we even leave the plate. All right. So I deleted this earlier. That was because I had accidentally not cleared it out beforehand, but let's make a graph. So I'm going to highlight the force. This is create the scatter plot using this data. To do this in Excel, you just do insert. There are different charts. In Google Sheets, you also use the same thing. It's charts. Use a scatter plot. That's the one that's preferred for this. You can use it with lines or marks with smooth lines, whichever you prefer. Both are acceptable. Sometimes it's nice to just change the legend around a little bit. Begins a little bit after one. Like, we can just make the minimum 0.5. Whoops. Yeah, 0.9 or so. All right. Just makes it a little bit easier to look at. Then you can change the title and so on. Just make sure you title it, if you want to title this, counter movement jump, force versus velocity. Yeah, that works. Or not force versus velocity, force versus time. Yeah, that works easy enough. So we have a few things to calculate jump height. Now to get jump height, we're going to do sort of an unorthodox way of getting it, but it works. We'll take kinetic energy at takeoff, and we're going to divide this by body weight. And why can we do that? Well, we're setting kinetic energy equal to potential energy, and then potential energy is mass times gravity times height. So if we if we divide kinetic energy by mass and gravity, we get height. So it works out nicely. But that would only get us how much the center of mass changes height. We also need to add the center of mass height at that time to it. So the center of mass travels to 1.392 meters. All right, great. And if you're so interested, you want to know, oh, how high did he actually jump? You know, how high did the center of mass move? You know, about 0.353 meters. So a little over a foot and, or let's call it like, what, 15 inches or so, I think. We can double check that. Almost 14 inches, you know. Wasn't anything spectacular. That's okay. All right, now we need concentric work. To get concentric work, we need to get the change in energy from when our center of mass is lowest compared to center of mass is highest of the total energy. Oops, jumped a little bit too far down. So let's double check where that 0 point happened in velocity. Velocity zeroed right here. Yes, center of mass here, velocity here. Eccentric, concentric. All right. So to get concentric work, we're going to take the total energy right before takeoff and then subtract it from when center of mass is bottomed out. Center of mass is bottomed out here. That's power here. Here is energy. So the change in energy was about 684 joules, 0.22 joules. Now let's get the phase time of eccentric. And this is going to be when eccentric ended minus when it started, or started movement here. And then concentric, 1 over, is when right before leaving the force plate, and minus eccentric turned over. There we go. So we can see eccentric time about 0.61, just about, well, not quite, but almost double the concentric phase time. So I took a little bit of time when I was in that eccentric phase. I did dip down a lot, about my center of mass height actually halved from 1 meter to just shy of 1.1 meters, sorry, versus 0.51, so it almost halved, nearly halved. All right, so if you have any questions, you can complete this document now. You should be able to. When you complete it, make sure you also turn in your data here with it, so I can check if there's any problem or anything like that. Just provides a good way of knowing, hey, this is what happened, seeing if something did happen or anything like that. But otherwise, if you do have any questions, please feel free to reach out. Otherwise, I will see you in the next video.